Hello and welcome to another video. Today we're going to be doing maximum number of coins you can get. And I think they kind of maybe thought that everyone was doing Thanksgiving, so they decided to give an easy problem that you could do pretty fast. So that's kind of funny. So there are n piles, or 3n piles of coins of varying size, and you and your friends will take coins. And basically what happens is you have 3 piles, or you have n piles. You get to pick 3 coins, and then out of those 3 coins, another person will pick the first coin, then you get the next one, and then another person gets the last one. And you're basically trying to maximize your total. So you have like this Alice, Bob, and me, and you want to try to maximize the number of coins you can get. So let's go through this example. So in this first one, you want to pick 2, 7, 8. And then what's going to happen is Alice will pick 8, you will pick 7, and then Bob will get 2. Then you pick this one, and Alice will pick the big one, you'll get the medium one, and Bob will get the small one. So your total here is 7 plus 4. 7 plus 2, which is 9. Second one, there's only one pile, so you'll get the medium one. And in the third one, this is the one we'll go through how to do. But essentially, anytime you pick a pile, you're always going to get the middle coin, right? Like someone will take the big one, you'll get the middle one, and someone will take the small one. And so basically they ask, like, what's the optimal strategy to do this? So right away, you can look at the constraints, and the pile's length is 10 to the 5th, which means you're looking for, once again, some kind of like 2-pointer or 1-pass type of like array solution. Not really looking for DP because n squared would be too slow. You might have like an easy second dimension which would work, but if you just had strictly n squared, that would be too slow. So let's figure out the optimal way to do this. So if we actually look at these early examples, basically because you always take the middle coin, ideally, what you want to do is you want to pick 2 coins that are close apart, right? So you want to give the first person like they're gonna get the bigger coin no matter what, but then you want to take a coin that's kind of close to that, right? And then the third coin you want to be as small as possible. So it's gonna be like first is biggest, second ideally is close to that, and then third is as small as possible, right? So this is one of these problems that you might get an intuitive solution and you might think like, oh, here it is. But when I first thought of it, I was like, okay, this has got to be like way too simple for a medium problem if you could do it like in this way. And it turned out it actually did work. So basically what you want to do, the easiest way to do this is to actually, because we want to like pick coins, like we want to know what's the biggest coin, what's the second biggest, and so on. We're going to want to sort these coins. And we can do that because this is 10 to the 5th, so and then log n solution would pass. So let's sort these coins and let's write out what those coins would be. So essentially we'd have 1 through 9, right? So 6. So basically there's no way for you to get coin number 9, right? Because no matter what pile you put it in, you will never get that. So essentially what you want to do, the strategy, it's really simple. You're going to pick 3 coins where 2 of them are the 2 biggest coins possible. So like these 2. And I thought this would be too simple, but then I couldn't really find a counterexample. So that's another thing. If you have a strategy that you think might work, try to draw it out and then try to see if you can find a counterexample. And then you can see if it fails. But in this case, I couldn't. So essentially, you just pick the 2 biggest coins for you and the other person because you want them to be as close to each other as possible, right? So what's the closest coin to 9? You can't get 9, but what's the closest coin to 9? 8. So you don't want to pick like 9 and 7 because then you'll get a smaller one. So you're trying to maximize for yourself. So you pick 9 and 8, and then the third coin you're not getting. So because like you're getting the second coin, the difference here actually matters, right? Like you want to get, like I said, you want these to be close to each other, but the third coin you're not getting, so you just want to pick the smallest one possible. So we would just pick 9, 8, and 1. That way, the first person would get 9. We can't get 9 no matter what we do, but we can get 8. And the way to get 8 is give the other person 9. And then for the third one, we just want to give the third guy the smallest one we can. So we would take these 3. So here, we would get coin number 8. And then similarly, out of everything that's left, we can't get number 7, no matter what we can do, right? There's nothing we can do to get 7, but we can get 6. And how do we get 6? We give the other guy 7. So we'll pick 7, 6, and 2. Now the third coin, I guess it doesn't really matter if you go like 9, 8, and 1 or 9, 8, and 2 and so on, but this will always lead to the best solution, and this is like the easiest way to do it. So then the second choice of coins, you can't get 7, but you can get 6. Best coin you can get. So we just pick 7, 6, and then what's the smallest coin available? 2. Now we get 6 here. Finally, we have 3, 4, 5 because that's just our last pile left. So 3, 4, 5, we will get 4. So we just get 14 plus 4, which is 18. And that's basically it. The intuition is just we can't get the biggest coin, but we can get the second biggest coin at all times. And the way to get the second biggest coin is take the biggest one. And then we want to have as many big coins left as possible for us. So then we'll give the third person the smallest coin possible. And here you go, we have 18. And that's actually basically it. So it's not a very hard problem. Normally when I come up with things like this, that are like pretty intuitive, there's usually like a bunch of edge cases that I just never thought of. And then I go and code it up in like 5 minutes and then it like doesn't work. But in this case it does. So that is good practice where you come up with some like greedy quote unquote solution where, and then you see if you can come up with a counterexample. That's good practice to see if you can actually figure out the edge cases yourself without actually like writing and seeing them. So in this case, there are none, so this just basically works. So essentially, pretty straightforward. How do we code this up? Well, really easy, right? So essentially, we just have a left pointer, right pointer. So we'll draw it like this. And while the left pointer is left than the right pointer, what do we need to do? We need to decrement the right pointer, simulating that this person, the first person took the biggest coin. We decrement it. We take whatever that is, so 8 in this case. Then we increment the left pointer. We don't really care about anyone else. We just care about ourselves, right? Classic. So we increment the left pointer. We do it again. Decrement the... So once we take our coin, we decrement the right pointer, so we're over here. Then for this person, they will take this coin. We decrement. We take this coin. We decrement again. And we increment the left because this person took this. Then finally, we take these 3. So same thing. We would decrement this. Take this coin here and increment this. This is just easy 2-pointer, right? You just decrement twice from the right and increment once from the left until your 2 pointers are passing each other. So pretty straightforward to code, and let's do that. So essentially, we're going to have a result. We're going to have a left and a right pointer. So we'll say left, right equals 0 piles. And we can just say while left is less than right, let's just kind of simulate this thing, right? So the first person will take the rightmost coin. So we'll simulate that by moving the rightmost index. Then we get to take the next one. So we will add that to the result. So we'll say result plus equals piles right. Now that we took that coin, we have to decrement that index again because that coin is no longer available. And now finally, the last person takes the leftmost coin available. So we'll simulate that by adding 1 to the left. And that's basically it. So I think we need to have this. So we can just return result, and that should be it. Oh, we forgot one more thing. We need to actually sort our coins, right? Because we need to know like what's the biggest available coin and so on. So I guess these aren't coins, these are piles, but same thing. Okay. And let's take a look. And here we go. We have an efficient solution. So pretty easy one, maybe a little bit tougher than an easy problem, just kind of like an intuition type thing. I was really thinking like how would I do this if this didn't work, because then it would get kind of tricky. Like how do I figure out like what's the other way to do it? But because this does work, it's pretty straightforward. So the time complexity here is going to be O of n log n because we have sort. The rest of it is 2-pointer, which is just O of n. And the space is O of 1. We didn't really need anything. We just needed 2 pointers. So once again, these are the things I would look for when looking at the constraints, right? C10 to the 5th. First, most common things to look for, some kind of 1-pass sliding window 2-pointer array traversal. And if you can't do that, then you have to look for harder stuff. And if this was less, like if this was 10 to the 4th, 10 to the 3rd, and so on, then I would maybe look at DP and things like that. But normally, you don't want to look at DP right away if your constraint's kind of big, because a straight up n-squared DP would be too slow. So hopefully you like this one. Pretty easy one for Thanksgiving. So happy Thanksgiving. And if you did like this video, please like it and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.